All right, thank you for coming. And we will celebrate Easter, which I don't. But anyways, by learning about some crypto. All right, so I'll try to be most of the part of the talk is I'll try to be as basic as possible. Towards the end, there will be a sudden speed up. So if you get lost in a sudden speed up, don't feel worried about it. As long as you come through with me for the basic part, you've already got a lot of mileage, I think, and I would be very happy. All right, so some of the slides, I used the idea from Goldwasser, and a lot of the slides I kind of worked over time with different co-authors, so I can't really credit them because they just get lost in the process. All right, zero knowledge. We're all theoreticians, we love proofs, we love theorems. And you think about the classical proofs, that there's lots of beautiful, beautiful theorems by great mathematicians that they prove things by writing things down, and then we can read the textbook and verify the correctness of those statements. All right, so these are actually, or if you think about, they are examples of this type of very simple, efficiently verifiable proofs. They have the common form that there are some statements, which is a claim that you want to prove. Say it's this equation, these two equations have a solution. And then the way that proof works is that there is a prover and a verifier. Now you can think about them as algorithms. Presumably, the prover is powerful and hardworking, where the verifier is weak and lazy. Okay? And the hardworking guy comes up with a solution, he solves the claim, and sends it over the solution. And now the verifier can simply check and accept if this solution is correct. Okay? Great. At the end of this interaction, very simple interaction, the prover simply gives the solution, the verifier is convinced. Okay? If this is a correct statement, he's convinced this is correct. And at the same time, the verifier learned the solution, a solution. Okay? Now I could ask, we've been doing this thousands of years, thousands. Is there any other way? Okay, just for fun of it. Is there any other way? In particular, is it possible that I can convince a verifier where he learns no solution at the end of it? Okay? And this is very much the goal of zero knowledge proofs. Here, roughly speaking, I want to prove to a verifier the validity of a statement. Now we're going to restrict ourselves, for the purpose of this talk, to only those statements that are in NP, meaning that there exists an efficiently verifiable solution. The prover wants to convince the verifier the statement is correct without revealing any information about the solution. Okay? Seems paradoxical. How is that even possible? Okay? We didn't just write the same proofs in textbook for thousands of years for no reason. All right. So, but nevertheless, let's try to do it anyway. So what are the properties we actually want from this system, this proof system? And then first of all, it should have correctness. If a statement is correct, then there is an efficient way for a prover to convince a verifier with probability 1. And I want soundness as usual. If a statement is false, then no matter how a prover, which may do arbitrary things, that's why we denote it as P star, no matter what he does, in the end, there is a verifier algorithm that is going to reject with very, very high probability. So here we're relaxing a little bit. Instead of saying verifier rejects with probability 1, we allow a very small error slack. Okay? And finally, zero knowledge, which intuitively what I want is that for any computationally bounded verifier, V star, again, this is a verifier that can deviate from the protocol and be arbitrary. Then he learns nothing from the interaction with the honest prover that follows the protocol.
So even if you say zero knowledge, you mean computational.
Right. Right now, I want to just have one definition. So this is in particular zero knowledge proof. We're going to see some variation of this definition later. Okay, but just keep one definition for now. All right, so the most interesting thing is, of course, how do we formalize this learn nothing, right? So in cryptography, we formalize using this simulation paradigm that Yuval and Manoj also touched on in the morning. that we consider the interaction between an arbitrary cheating verifier who do whatever he wants with the only constraint that he is computationally bounded, polynomial time. And he interacts with honest prover verifying a proof. So in this interaction, he sees a few things. He sees messages, and he could toss some random coins. So his whole behavior, given this code, is completely determined by the messages and the random coins. Okay? We're going to denote this as a special random variable called real view. And it just contains all the message and random coins of the verifier. We would like to say that in this real interaction, the view of the verifier actually contains no information. How? In the sense that there exists a simulator which knows only the statement but not the solution. It knows no solution at all. But yet the simulator doesn't engage in any interaction. All what he does is does a bunch of computation in its head, and in the end he spits out an output. And the output is supposed to be this random variable. We call it the sim view, in the sense that its goal is to produce an output that looks like a view of the verifier in the real world. Okay? So in particular, the output should also contain a bunch of messages, some random coins. So what we would like to say is that this simulated view should be very close to the real view. In other words, you should say that the distribution of this random variable that describes the message and random coin of the verifier in the real world and the distribution of the output of the simulator are very close. Okay? So how do we formalize two distributions very close? We've seen a bunch of different ways. You could think about their variational distance or statistical distance being very small. Or usually, in crypto, whenever computational assumption is involved, we have this computational indistinguishability that says that for any polynomial time distinguisher, this is also the environment in the talk in the morning, that he gets a sample from one of the two distributions and creates an output which is a single bit. The probability that this bit, the output of the distinguisher being 1, is really, really close in both cases, in the two cases. Okay? This is just kind of a generalization of statistical distance by restricting the unbounded distinguisher to computationally bounded distinguishers. All right. So once you buy this definition, you can, for the rest of the talk, you can more or less just forget about this concrete definition. Just think about that the two distributions, real view and the simulated view, are very close.
If you want to think of it as an environment, shouldn't the distinguisher also get W? Because the environment sees
But you're quantifying overall except the...
Exactly. Because I haven't shown the order of the quantifier. You're right. So what happens is that we want this view to be very close to happen for any verifier. And for any verifier, there exists such a simulator that is going to work for that verifier. And the simulator is supposed to work for any statement and witness. And by saying the viewer indistinguishable, it means implicitly means that the distinguisher knows the statement and the witness. All right. Is it very clear? Okay. So a bit complicated now. But all in all, what it says is that what is zero knowledge? How do you say that the interaction conveys no information? It means that if you can simulate, one might well stay at home. Okay? No need to interact with anyone, go out and send messages over and over. Just lay down at home and think about a simulated view. Okay?
Except for one bit, right?
Except for one bit, yeah. So clearly, the simulator needs to depend on the verifier, because for every verifier there exists a simulator. Okay? And in the rest of the talk, one bit of distinction between different, so how could you construct this type of simulator? How does the simulator depend on the verifier? There's one bit of a distinction that is going to become important, which is whether the simulator depends on the verifier in a way that involves its code or not. Okay? So we can think about black box simulator means you can think about the simulator as having access to the verifier, meaning this algorithm, but it doesn't really care about how exactly this algorithm is implemented. How it depends on is that it's going to kind of interact with this algorithm by sending a message and seeing its response. In this way, it could create a view that emulates the real view. Or in the other case, the stronger, more general case is a non-black box simulator that actually do care about what is the code of the verifier. Okay? In that case, we call it a non-black box simulation. Okay? All right, so this is the only distinction I'm going to make later in the talk. So far we've seen a definition, which is a zero-knowledge proof. Recap again, we care about soundness holds no matter how, even for unbounded, no matter how the prover could cheat. And zero-knowledge, we only talk about it with respect to bounded verifiers. Okay, so this is zero-knowledge proof. A weaker version of it is that, well, since we're concerning only polynomial bounded verifier, why not do the same also for the soundness? Okay? How about relax the soundness to computational version that I only care about bounded time, polynomial time provers to cannot prove cheating a false statement. Okay? In this case, to make the distinction, we're going to call it a zero-knowledge argument as opposed to a zero-knowledge proof. Okay? We could also consider a stronger version, which is a variation for the zero-knowledge part, that instead of considering bounded time verifier, we could also think about unbounded time verifier. Could argue about that a proof system leaks no information even if the verifier is unbounded time. In that case, then the zero-knowledge property gets lifted up to statistical zero-knowledge, and again you can think about the two versions of computational soundness or statistical soundness. And for the purpose of this talk, to not get myself into too many difference, I'm going to ignore the statistical version. Okay? For me, there only exists zero-knowledge proof and zero-knowledge argument. Okay. All right. How? This is great. It looks like something completely different from those classical proof we've been doing for thousands of years, but is paradoxical? Is it possible? Now I'm going to tell you some basic protocols. The way that it does is kind of like, all right, so I'm going to prove to you, but I'm not going to give you a solution. But I will prove to you that I could give you if I feel like it. Okay? In the end, you'll be convinced that I could actually give you a solution, but without giving you a solution. Okay? So for the next part, I'm actually going to use the board. And feel free to interrupt me.
This is like from us last year.
Huh?
This is like from us last year.
Last year. Oh, yeah, exactly.
Next time we'll be using
All right, so the first protocol I'm going to talk about. So this part about the basic protocol, I really hope everyone can follow. So if you have any problems, questions, just interrupt me. Okay? So let's think about proving the type of statement, which is y is a square mod n. Okay? So this is my statement. What is the solution for this statement? Well, clearly it's the square root of y mod n. Right? So the solution should be some alpha such that y equals to alpha square mod n. Now, we're thinking about that a prover would like to prove that y is a square to a verifier without actually telling the verifier alpha. The way that we're going to do it is kind of like we're going to create a secret share of this statement and this solution. This is just a convenient way to think about. What does that mean? I'm going to create x0, w0, and x1, w1 in the following way. What is x0? x0 is just going to be some random z I'm going to pick a random beta, random from Zn. I'm going to compute Z as beta square mod n. Okay. So what does this pair mean is that here I have a new statement, which is that Z is a square mod n, and this statement has a solution, which is beta. Clearly, I created it. Now I'm going to create another statement, which is Z multiply Y is a square mod n. And what is the solution to that statement? Well, if you know about alpha, then it's easy to create a solution for Zy, which is simply going to be alpha beta, right? Alpha beta is going to be the square root of Zy, right? So now, why is this a secret share of an x and w? Because that if you learn about both beta and alpha beta, clearly you can reconstruct a solution for y. Clearly you can know alpha, right? But if we look at the distribution of z and beta alone, well, this is just a uniform beta and squared. If I look at the marginal distribution of zy and alpha beta only, again, this is just a random element from Zn and it's square. Right? So clearly, each of the share their distribution, I can easily simulate it myself, right? And it reveals no information about alpha at all. Okay? But yet together, they're going to reveal alpha. So now that I have this secret share, think about what a prover should do, right? What the prover care about is that I am going to create this share of x0 and x1, and I'll tell you that here are my two statements. x0 is z, x1 is zy. Right? I'm not going to tell you a solution to both of them. If I tell you, then you learned about my solution alpha. So I'm only going to tell you one of them. Which one? You pick. Okay? So the verifier gets to pick which solution he wants. He sends a single bit b, and according to his choice, if b equals to 0, p is going to give the solution w0, which is beta. If b equals to 1, p is going to give the solution w1, which is alpha beta. And the verifier, no matter in which case, can easily verify whether beta is a correct solution for z or whether alpha beta is a correct solution for zy. And if that's correct, then he accepts. Okay? Intuitively, why is this zero knowledge? It's zero knowledge exactly because no matter what is the choice of the verifier, he gets only one pair. And getting a single pair, the distribution, reveals no information about alpha. Okay? So this is kind of a very neat idea about giving you a proof, but by this probabilistic choice, essentially, P proved to verifier that I have the capability to give you a solution, I'm just not giving it to you. Okay? So this is already very close towards getting a zero knowledge for general NP languages, except not quite, because this type of statement is not necessarily NP complete. Okay? So what I'm going to do now next is that I will show you a protocol for NP complete language of graph homotonicity. And if we have that, then by the general NP reduction, we will have a zero knowledge for any language in NP. So what is this language? It concerns about those graphs which call Hamilton graph. It's a graph that contains a Hamiltonian cycle. What is a Hamiltonian cycle? It is a cycle that goes through all nodes in this graph. Okay? So in all those example graphs, the red cycle is a cycle in particular goes through all nodes and hence a Hamiltonian cycle. So the language, this is an NP complete language which contains all those graphs which are Hamilton graphs. The question is the following. Given you a graph, tell me whether it is a Hamilton graph or not. Okay. So the statement is going to be a graph, and we're going to describe it using its adjacency matrix. And the solution to a true statement is simply the position or the edges that are on this cycle. Okay, this is a solution. If I tell you what are the edges on the cycle, you can easily verify that this is a Hamiltonian cycle. Okay. All right. So let's see that for this type of statement, how can we construct a zero knowledge proof? So first of all, as an example, if I have a graph like this, then I can represent it using its adjacency matrix, denoted as mg, which simply indicates at every position whether that position, the ij's position, corresponding to an edge in the graph or not. Okay? So for this example, we know 1 is connected 2, 3, 4. So the first row is going to be 0, 1, 1, 1. And the rest can easily verify. This is a corresponding adjacency matrix. Okay? So this is going to be how the statement looks like. How does the solution look like? Well, the solution, as we said, is just the position of the cycle. So in this case, if the cycle is this one, it will just be contain all the edges 1, 3, 3, 2, 2, 4, 1, 4. And these edges, actually, if we go back to look for them in the adjacency matrix, it's going to be something like 3, 1, 1, 1. Okay? So you can find out the cycle in the adjacency matrix, which is going to just be exactly sort of a permutation inside the adjacency matrix. All right. So now just generalize this type of statement. Again, we have a graph together with a solution, which is the cycle inside this graph. Now I want to prove it, and I want to use the same idea as we saw before, is I want to secret share this statement and its solution. Okay. How do I secret share it? Well, the first share, what I will do is I will just create a random permutation of this graph. What does a random permutation mean? It means I'm going to randomly permute the nodes. Okay? I pick a permutation, pi. In the example, it's going to be from 3 to 3, which is going to simply rename all those nodes. Okay? So say 1 is now, the first node is now the second node, the third node is now the first node, fourth node is now the third node, and the second node is going to be the fourth node. Okay? By permuting the nodes, it creates a new graph. If you think about it, its adjacency matrix is going to change. Okay? So the statement 0 is just a random permutation of the graph. And what that statement is about is that I want you to show me that this random permutation is indeed a permutation of the original graph G. What's the solution? Well, the solution is the permutation itself. If I give you the permutation, you look at this pi of G and G, you easily verify that they are indeed a permutation of each other. Oh, so far I've done nothing. What is the second statement? The second statement is going to be involving pi of G again, but now proving something for real. Okay? Second statement is pi of G is a Hamilton graph. Well, what is the solution for this? If I know the cycle, the position of the cycle in the original graph, and I know about the permutation, easily I can come up with a solution. How? I just correspondingly permute all those nodes in the cycle that I know about before. After renaming the nodes in the same way, this is going to be a cycle in the new graph, in the permuted graph. Okay? Now let's see whether this is a secret share like the last case. Clearly, if I'm giving you x0, w0, x1, w1, you learn about the cycle, right? Why? Because you know about the permutation, so you can just permute this cycle back. It's going to become a cycle in the original graph, correct? If I look at the marginal distribution of x0, w0, it's totally unrelated with the original graph and the cycle, right? It's just a permutation. Now, if I give you x0 and x1 and w1, I don't know, right? Suppose the random permutation, it's hard for me to map a random permutation back to its original graph. Say it's a graph isomorphism is hard. Then maybe it reveals no information. But that's not the case, right? We know graph isomorphism is easy. Not really, but it's closer to the easy region than the hard region now by the recent breakthrough. Okay? So I don't know, in particular, if G is something odd, it could totally be that I could map it back. Then learning this cycle is fatal. But we haven't done nothing, because suppose now I didn't give you. Suppose that instead of looking at x1, w1, I only look at w1 alone. I look at the marginal distribution of w1. Then again, just seeing a permutation of a cycle gives you no information about the original cycle. Okay? So now the rough idea is that I'm going to create this sort of game like before. In the case b equals to 0, you get x0, w0 both. In the case b equals to 1, you don't get x1. You get the w1 alone. Then it's again zero knowledge, correct? All right, so let's see how it goes. So the first change in the protocol is that I cannot afford to give you directly pi of g. Why? Because if I give you pi of g, in the case of b equals to 1, I would get stuck. Because he will see both w1 and x1, and it might not be zero knowledge anymore. Therefore, I'm now working a word where I use this physical assumption that there exist those sealed envelopes. Allow me to now think about this protocol instead of digital. Think about it's a physical game between two persons face-to-face playing this game. What now we can do is that instead of giving pi of g in the plane, we create this adjacency matrix of pi of g, and we're going to put each of the entry, seal it inside an envelope. Okay? So now what the verifier sees a bunch of envelope. Great. Now he makes a choice. He says that, okay, I want to see either 0 or 1. In the case of 0, what P does is that he needs to reveal both x0 and w0. How he does that? He can give out the pi and open OR envelope. If he opens OR envelope, effectively that V sees pi of g. Therefore, he gets both pi of g and pi. Now, if b actually equals to 1, what he does is that he's not going to give out, he's not going to open all the envelopes. What he wants to do is to only reveal w1, right? Therefore, he's going to only open these envelopes that are on the cycle in pi of g. Remember that whenever we have a cycle, they simply corresponding to some entries in the adjacency matrix. So how do I open up to a cycle? Well, I know the position of those edges that are on the cycle, and I simply open only these envelopes. So in the end, you will see that a few of those envelopes are opened, the others remain sealed. the verifier can easily check that whether those envelopes actually are these open envelopes corresponding to a cycle in the graph or not. Okay, correct? All right. So think about it. Why is this sound? Why no prover can cheat? It's because that as soon as the prover gives out all those sealed envelopes, he has effectively committed to which graph he is sent. The only difference is that he commits to it, but the verifier doesn't learn about it. It's still hidden from the verifier. So if he is talking about a graph that doesn't have a Hamiltonian cycle inside, okay, then he must fail in one case. Either the graph he has committed to is not a permutation of G, or that graph doesn't have a cycle. Okay. Therefore, he must fail in one of the cases, either b equals to 0 or b equals to 1, and the verifier, by randomly choosing the choice, will be able to catch him with probability 1. Okay. So the soundness or error is exactly half. Okay. Does it make sense? All right. How much time do I have left?
20 minutes.
Okay. All right, so great. So this is not exactly what I promised you, because what we would really like is a completely digital algorithmic protocol instead of using any physical assumptions. But as you can see that up to now, it's completely information theoretic, right? All the arguments I made are information theoretic. So what happens in cryptography is whenever we get stuck with respect to information theoretic argument, we cannot move beyond that, we throw in a computational assumption. Okay? So how do we implement those sealed envelopes? We're going to use this cryptographic primitive called the commitments, which are exactly the analog of sealed envelopes. It allows a committer to commit to a value, which is the equivalent of putting a value into a sealed envelope. And the guarantee is that the value is hidden. Okay? No matter what the value put in, a bounded receiver cannot tell. On the other hand, later, the committer can decommit by giving out what is the value committed to and some additional information. And the receiver can actually check, verify. The guarantee here is the binding, which is exactly like opening a sealed envelope, that once you have put a value into it, there's only that value that can come out. And this is guaranteed by any string. There exists a unique value v that the committer can open it up to. So as you can see, this is exactly the analog of sealed envelope. And therefore, as soon as you throw that in,
So you say that any string is a commitment of some value. Is that right? I mean, so
there's at most, sorry, yeah. Instead of saying exist, I should say at most, yeah. Okay. So now the digital protocol is simply replacing all the sealed envelope with the commitments. Okay. And the rest is the same. The verifier can choose which solution he wants to see, and depending on his choice, either I open up the entire adjacency matrix and give the permutation, or I only open up those commitments that are on the cycle in the permutated graph. Great. So as you can see, that zero knowledge. Simulation is entirely black box. I didn't really go into the simulation, but as you can imagine that to simulate either W0 or W1, you really do not care about the code of the verifier. Right? It doesn't matter what is the code of verifier, I can simulate those distributions. Okay? And it is statistical sound, I'm not, just like in the physical case. Great. So there's only up to one problem. So this is a zero knowledge proof up to one problem. That is, the soundness error is still quite high. The soundness error is something roughly half. Okay? So how can we reduce this soundness error? There are different ways to approach it. The easiest is a sequential repetition. Okay? Simply play this game for multiple times. What is happening here is to sequentially play this game for n times, and soundness error is going to go down exponentially. And the zero knowledge still remain. Why? Because essentially you can simulate each of the gameplay individually, one by one. A better way that you could people naturally will want to approach it is, instead of repeating it sequentially, that makes the protocol really long, I would like to just repeat in parallel, right? Play this game between the prover and the verifier for n times in parallel instead of sequentially. Okay? Unfortunately, Sunday's error would go down just like in the sequential case, but zero knowledge breaks. Okay? Why would zero knowledge break? Essentially, is because when you have all the executions in parallel, somehow the simulator will have to try to guess what is the choice of the verifier all at once. In the case of sequential repetition, you guess one at a time. However, in the case of parallel repetition, you have to guess n altogether, and that makes the probability really low. Okay? If you don't get it, it's okay. Yeah, just think about the sequential case. Somehow the best we could do with respect to this type of protocol is kind of a hybrid between both sequential and parallel repetition. And that would actually give you a protocol that has negligible soundness error, and the round complexity is omega-1 round. Okay. So today we know actually much better. In fact, today we know that everything possible is provable in zero knowledge efficiently. There are, in fact, even practically efficient protocols exist. The best in terms of round complexity we know is that there exists a 4-round zero knowledge argument, and there exists a 5-round zero knowledge proof. So the question is, are we done? Right? And what I claim, yeah?
So you said zero is argument. Up to this point, whatever you said was a proof.
Yeah, whatever I said so far is a proof. Yeah. Not quite. Why? So far, what we consider zero knowledge is in this standalone model where we have one, in particular 2 players, 1 prover and 1 verifier, running 1 protocol at a time. Okay? But in real life, especially if you think about deploying zero knowledge in the internet for different purposes, then it's going to be concurrent. At any point of time, there are multiple sets of players running multiple protocols all together. This is in some sense the composition of a cryptographic protocol that Yuval also mentioned in the morning. And in this case, what we really want is we want this, what we call concurrent zero knowledge. In fact, one of the inventor, oh, actually, Moni is not here. Yeah, okay. One of the inventor, Caesar is actually sitting here, right? So the concept of concurrent zero knowledge is that what happens if a verifier is not just receiving 1 proof? What happens if it receives multiple proofs simultaneously? Okay. Does he learn something more now? And in particular, we allow the verifier, he is interacting with, think about it, interacting with a single verifier, interacting with multiple provers, and he could completely control the timing of the messages that in all those executions. Okay? He decides, that's the strongest we could think of. He decides when to send the next message he wants, and the honest prover would immediately send back the response. So in this case, naturally, I would like the zero knowledge property to compose naturally, in the most natural sense. In the sense that whatever the verifier sees in these multiple proofs, I would like to say that jointly he learns nothing. He learns nothing from all those joint executions. How do we, yeah?
What about the other provers learning things about the other provers? Is there like a block where, since the verifier doesn't know?
Yeah, because the verifier doesn't have any valuable information. So we're not concerned. Zero knowledge is very one-sided in the sense that we're only concerned about the W. Okay. So in this case, naturally, we would like to have a definition that says the simulator, who knows only about the statement, is able to reproduce or simulate the entire view in all those joint executions. Okay? So this is the most natural generalization of zero knowledge property. And here again, we would like to say that for any verifier, there exists such a concurrent simulator that can create this, simulate the view that is indistinguishable from the real. So what do we know about concurrent zero knowledge. It turns out that the hardness suddenly goes up. It's much harder than zero knowledge. The best we know, more or less, not really the best. For a very, very long time, the best we know is a protocol that has logarithmic number of rounds. In contrast, in zero knowledge, we have very short number of, a few number of rounds protocols. And what's even more surprising that it turns out this is more or less tight. In the sense that if you think about those zero knowledge protocols, that admits a black box simulation. The simulator doesn't depend on the code of the verifier. Then concurrent zero knowledge argument must have logarithmic number of rounds. Okay? And in fact, this lower bound is not just only for concurrent zero knowledge. Similar lower bound exists for even standalone zero knowledge. In the case of black box simulation, zero knowledge argument needs to have more than 3 rounds. Zero knowledge proof needs to have more than 4 rounds. Unless your language, the language you're proving, is something very simple, either inside the BPP or inside the co-MA. Right? So ignore it, just think about for general MP, that you cannot go beyond the 3 round or 4 round. Looks great, right? We have a very complete picture. Right? We know very much, more or less everything tied for black box simulation. But if you think about it, we can just turn all of those questions, the lower bound, into a question now. Question is, okay, can I have a 3 round zero knowledge argument with non-black box simulation that actually uses the code of the verifier? Or a 4 round zero knowledge proof, non-black box simulation? Or let's think about a very ambitious goal, a constant round concurrent zero knowledge argument with non-black box simulation. And all of those questions, we actually know very little about. Okay? In fact, so far, we had some very partial progress in terms of the first and the third problem. One from this type of knowledge assumption, very non-standard assumption. The other is from indistinguishability of fuscation, which is very popular recently, but still a very, very strong assumption. Nothing like what we used to know, one-way function, or here, the collision-resistant function suffices. So in all those questions, from standard assumption, standard and weak assumption, we have no answer. Okay? So in this view, we know actually very little about non-black box simulation. So my plan is to tell you about this kind of, I have 10 minutes? Okay. All right, so let's just go. All right, so why do we know so little about non-black box simulation? It turns out that in terms of upper bound or designing protocol, there is essentially only one protocol that we know that uses non-black box simulation, and all others are variants of it or derivative of it. So let me try to tell you about it. It's also, again, a very basic, but very, very clever protocol. So if you get that, also a big pat on my shoulder. All right, great. So this protocol is going to use 2 tools. One is, again, a commitment, but a slightly stronger commitment, which we call succinct. For those who you know, it means that no matter how long the committed value is, the value I put into the sealed envelope, the commitment string is always very short. Okay? But for those of you who don't know, just think about it as a commitment as we have talked about. It's a sealed envelope. Okay? The other tool is what we call a witness indistinguishable argument. Well, argument we know. The universal part, again, which is like the succinct part, no matter how long your statement or your witness is, the protocol is very short. All messages are fixed length. So what is witness indistinguishability? It's essentially just a weaker property than zero knowledge, which says that, well, I don't ask you to say the verifier learns nothing about the witness. He might learn something about the witness. But at the very least, I want to guarantee that if he is interacting with the prover using one witness for one statement versus the prover using a different witness for the same statement, just sometimes the same statement may have 2 different solutions. If I prove to you using one solution versus another solution, you can't tell apart. But beyond that, you might learn something about the solution through the interaction. It's just that you can't tell whether it is solution 1 or solution 2. Okay? In other words, in those two real words with one witness versus another witness, the view of the verifier are indistinguishable. Okay. Great. So, what is the Barak's non-black box zero-knowledge protocol? Well, the protocol is actually very simple and looks somewhat similar to what we have seen. What it happens is it has the form, prover sends a commitment at the beginning, the verifier sends a random string, and the prover gives a witness indistinguishable proof. Okay. For the purpose, let's always think about that. The commitment in the first message is either a commitment to 0 or it's a commitment to a machine. Yeah? Yeah, of course.
So, weak indistinguishability and zero knowledge seem very similar to me. Can't you just fix one W1 and say that?
Right, so what happens is that if it's a statement that have two witnesses, actually this gives you zero knowledge. Because if you can learn something, you can potentially. But what happens is that you could have those statements that have only a single witness. Then WI give you no guarantee in those type of statements. In that sense, it's weaker than zero knowledge. But somehow, construction-wise, this is much easier. All right.
Did you say that if there are two witnesses, it implies zero?
In some sense, it is right, because if you know one of the witness, you can simulate using the other witness. It's kind of like a commitment. So if you know that, if you know that the commitment, the indistinguishability definition of a commitment, which is commitment to 0, commitment to V versus commitment to V prime are indistinguishable. Right? So if you have kind of a WI, and if it happens to be that you know one canonical witness, then you can always simulate.
But you might know information.
Yeah, I might not know. Right. That's true. That's true. Okay, then it's not.
Zero knowledge with an unbounded simulator. That's a precise.
Exactly. That's true. It's a zero knowledge with unbounded simulator. Because unbounded simulator can always find a canonical witness. Yeah. Right. All right, so let's go on. Think about that. The commitment is either a commitment to a 0 or a commitment to a string that could be passed as a machine, okay? An algorithm. You could view it as an algorithm, just like any algorithm, you can write down it as a string. And then, what is the final WI trying to prove? It's trying to prove a statement that either the statement you want to prove about is true, or that the string C actually commits to a machine M that have a special property. What is that special property? The property is that when it's M, there exists a very short input to this machine M, so that when M receives that input, it's going to produce exactly the challenge R from the verifier. Okay? Very bizarre. Okay? You're going to see why this is set up. Okay? So in some sense that, and one thing that we need to note very carefully is that, as we denote in the picture, is that the length of the message are different. For the purpose of this talk, you can think about always that the commitment and the final WI have fixed length n, and then in this case, the challenge from the verifier R is going to have length 2n. Okay? So basically, the length of the R needs to be n, needs to be the length of the commitment plus n. Okay? All right. So the neat thing about the protocol is that it really has two phases. This protocol has two phases. It has the blue phase, which is kind of a very benign phase, that the prover commits to 0, receiving this R, doesn't care about it, and simply prove in the end that the statement is true. Okay? But it also has a very bizarre phase, which is the red phase. The red phase is that it's trying to commit to some machine that is going to predict R. Okay? And it's going to predict R only given a very short input, much shorter than R itself. It's going to get a short input that has some length, which is n shorter than R. Okay? This is the bizarre phase. So exactly the honest phase is going to be used by a real prover who knows about the witness. And clearly the bizarre phase is going to be used by a simulator who knows nothing about the witness and must cheat in somehow. Right? Correct? So why is this protocol sound? Essentially the soundness boils down to say that any computationally bounded prover can only go about the honest phase, can only use the honest half of the protocol and cannot use the dishonest half. Why is that? Well, let's think about it. If he wants to use the dishonest half, what he needs to do is that he needs to first commit to a machine that is going to predict R given some short input. But R is completely random, right? So it has 2n bits of entropy inside it. How is it possible that one could commit to a machine before seeing these 2n bits? And this machine has a property that only receives n bits of the input, which contains at most n bits of the entropy, but then this machine is going to produce this 2n bit random string. Okay? This 2n bit random string has very high complexity, and it cannot be possibly conveyed by using only an n bit input. Okay? Therefore, in that sense, information theoretically, if this commitment is statistically binding, then information theoretically you cannot cheat. Of course, this commitment is not statistically binding. But nevertheless, for a computationally bounded prover, for this reason that he cannot use the trapdoor phase and hence must prove honestly that the statement is true.
Why is the commitment not statistically binding? You could use one.
Because I require it to be succinct. Okay. Does that make sense? Okay. All right, great. So here comes how possibly a simulator could make use of the code of a verifier. If you think about it, it's quite remarkable because we don't have any good algorithmic ways of understanding the code, any code, right? So the way that it can use the code of the verifier is to simply not understand it at all. Don't try to understand it. I'm just going to use the code itself to predict its next message. At least that I can do without understanding the code, right? So what the simulator is going to do is obviously it's going to use this trapdoor phase, right? What he can do is he knows about the code of the verifier, so he could simply commit to it. Okay? By committing to the code of the verifier, and afterwards the verifier sends its random challenge, now the prover can cheat in the final proof that the code he commits to, which is V star itself, on some short input. What's that exactly that input? The input is exactly the commitment itself. Okay? Because V star on the commitment outputs the random challenge. Okay? Therefore, the prover can simply set his sort of the fake solution, which is the V star itself, and the input is the commitment itself. And he can prove to the verifier that this code, V star on input C, outputs R, which is a tautology by definition. Okay. So the way the simulator uses the code of the verifier is to not understand it, and let me just use it to predict its next message. Okay. A cheating prover cannot do so because it doesn't know what is the code. On the other hand, a simulator can. Okay. All right, great. So why is this zero knowledge? It's exactly because that the honest half and the cheating half are indistinguishable. Why? Because the commitment is hiding, so he has no idea whether it's committing to 0 or M. And on the other hand, WI makes sure that no matter which witness I am using for the same statement, the computationally bounded verifier cannot tell. So in other words, honest half and cheating half are indistinguishable. All right, great. So 2 minutes?
1 minute, negative 5 minutes technically.
All right, so I'm going to skip the part about concurrent zero knowledge, but maybe just tell you about the statement that what we know the best about concurrent zero knowledge today. Right? So this is just a completely beast, a complete independent beast on its own, related but a beast. All right, so what do we know about it? In terms of, so the hope is, of course, that we know there is a lower bound for black box simulation concurrent zero knowledge, that we cannot go below logarithmic round. So the hope is that this, we're not using black box simulation. We're really utilizing the code of the verifier. Maybe this type of simulation could help us to break the lower bound, okay, to circumvent the lower bound. So the best we know so far are using a tool which we call p-certificate. Okay? What is a p-certificate? Very roughly, so there are different variants of it, and we can use them to all construct concurrent zero knowledge. And specifically, in one branch, if you allow the p-certificate to be two-round and unique, we can actually implement it using indistinguishability of fustigation. Okay, so very briefly, what is a p-certificate? I don't have to. Okay, all right. So let me just show the final statement. All right, so this is the theorem. What we know today is that we could actually have a one-round concurrent zero knowledge using indistinguishability fustigation, one-way permutation and collision-resistant hash function. And then we can get around the lower bound. Right? So still an open problem that whether we can do it without I/O using some more standard assumptions, for example. 6. Not bad. All right, thank you.